Out of my latter years, psychologically connected with the heart as an assigned body, the bold notion of space which preceded all scientific geometry transformed our mental concept of the relations of position of bodily objects into the notion of the position of their bodily object in space. This, on itself, represents a great format simplification. Throughout this concept of space one reaches, moreover, an attitude in which any description of position is admittedly a description of contact, the statement that the point of a bodily object is located at a point P of space means that the object touches the point P of the stand and the body of reference B0. Supposed, appropriately continued, at the point considered. In the geometry of the Greeks, space plays only a qualitative role, since the position of bodies in relation to space is considered as given. It is true, but it's not described by means of numbers. Descartes was the first to introduce this method in his language. The whole content of Euclidean geometry can axiomatically be founded upon the following statements. 1. Two specified points of a rigid body determine a distance. 2. A coordinate three plates of number x1, x2, x3 to points of space in such a manner that for every distance p primo 1p secondo under consideration. The coordinates whose endpoints are x primo 1, x primo 2, x primo 3, x secondo 1, x secondo 2, x secondo 3. The expression s square equal x secondo 1 minus x primo 1, the whole square plus x secondo 2 minus x primo 2, the whole square plus the x secondo 3 minus x primo 3, the whole is square, is independent of the position of the body and of the position of any and all other bodies. The positive number S means the length of the stretch of the distance between the 2 points P primo and P secondo of space, which are coincident with the points P primo and P secondo of the stretch. The formulation is chosen intentionally in such a way that it expresses clearly not only the logical and axiomatic, but also the empirical content of Euclidean geometry. The purely logical axiomatic representation of Euclidean geometry has, it is true, the advantage of greater simplicity and clarity. It pays for this, however, by renouncing representation of the connection between the notional construction and the sense experience. A with connection alone, the significance of geometry for physics rests. The fatal error that the necessity of thinking preceding all experience was at the basis of Euclidean geometry and the concept of space belonging to it. This fatal error arose from the fact that the empirical basis on which the axiomatic construction of Euclidean geometry rests had fallen into oblivion. Insofar as one can speak of the existence of rigid bodies in nature, Euclidean geometry is a physical science, the usefulness of which must be shown by application to sense experiences. It relates to the totality of laws which must hold for the relative positions of rigid bodies independently of time. As one may see, the physical notion of space, also as originally used in physics, is tied to the existence of rigid bodies. From the physicist's point of view, the central importance of Euclidean geometry rests in the fact that its laws are independent of the specific nature of the bodies, whose relative position is discussed. Its formal simplicity is characterized by the properties of homogeneity and isotropy and the existence of similar entities. The concept of space is, it is true, useful, but not indispensable for geometry proper, for the formulation of rules about the relative positions of rigid bodies. In opposition to this, the concept of objective time, without which the formulation of the fundamentals of classical mechanics is impossible, is linked with the concept of the spatial continuum. The introduction of objective time involves two statements which are independent of each other. The introduction of the objective local time by connecting the temporal sequence of experiences with the indications of a clock of a closed system with periodical occurrence. 2. The introduction of the notion of objective time for the happenings in the whole space, by which notion alone the idea of local time is enlarged to the idea of time in physics, not concerning one. As I say it, it does not mean a partitio principii if one puts the concept of periodical occurrence ahead of the concept of time, when one is concerned with the clarification of the origin and of the empirical content of the concept of time. Such a conception corresponds exactly to the precedence of the concept of the rigid or quasi-rigid body and the interpretation of the concept of space. Further discussion of 2. The illusion which prevailed prior to the enunciation of the theory of relativity, that from the point of view of experience the meaning of simultaneity in relation to happenings distant in space, and consequently that the meaning of time in physics is a priori clear. This illusion had its origin in the fact that in our everyday experience we can neglect the time of propagation of light. We are accustomed on this account to fail to differentiate between simultaneously seen and simultaneously happening, and as a result, the difference between time and local time fades away. The lack of definiteness, which from the point of view of empirical importance adheres to the notion of time in classical mechanics, was valid by the axiomatic representation of space and time as things given independently of our sense. Such a use of notions independent of the empirical basis to which they owe their existence does not necessarily damage science. One may, however, easily be led into the error of believing that these notions, whose origin is forgotten, are necessary and unalterable accompaniments to our thinking, and this error may constitute a serious danger to the progress of science. It was fortunate for the development of mechanics and hence also for the development of physics in general that the lack of definiteness in the concept of objective time remained obscured from the earlier philosophers as regards its empirical interpretation. Full of confidence in the real meaning of the space-time construction, they developed the foundations of mechanics which we shall characterize schematically as follows. A. Concept of a material point, a bodily object which, as regards Its position and motion can be described with sufficient exactness as a point with coordinates x1, x2, x3. Description of its motion in relation to the space b0 by giving x1, x2, x3 as function of the time. B, or Bravo law of inertia. The disappearance of the components of acceleration for the material point, which is sufficiently far away from all other points. C. Law of motion for the material point, force equal mass x acceleration or mass factor acceleration. D. Law of force, actions and reactions between material points. In this B is nothing more than an important special case of C. A real theory exists only when the laws of force are given. The forces must in the first place only obey the law of equality of action and reaction in order that the system of points permanently connected to each other may behave like one material point. These fundamental laws together with Newton's law for gravitational force form the basis of the mechanics of celestial bodies. In this mechanics of Newton, and in contrast to the above conception of space derived from rigid bodies, the space B0 enters in a form which contains a new ID. It is not for every B0 that validity is required for a given law of force by B and C, but only for a B0 in the appropriate condition of motion, inertial system. On account of this fact, the coordinate space acquired an independent physical property which is not contained in the purely geometrical notion of space, a circumstance which gave Newton considerable food for thought. Pay experiment. Classical mechanics is only a general scheme. It becomes a theory only by explicit indication of the force laws. D, as was done so very successfully by Newton for celestial mechanics, from the point of view of the aim of the greatest logical simplicity of the foundations. This theoretical method is deficient in so far as the laws of force can't be obtained by logical and formal considerations, so that their choice is a priori to a large extent arbitrary. Also, Newton's gravitation law of force is distinguished from other conceivable laws of force exclusively by its success, in spite of the fact that today we know positively that classical mechanics fails as a foundation dominating all physics. It still occupies the center of all of our thinking in physics. The reason for this lies in the fact that regardless of important progress reached since the time of Newton, we have not yet arrived at a new foundation of physics concerning which way be certain that the whole complexity of investigated phenomena and of partial theoretical systems of a successful kind could be deduced logically from it. In the following lines, I shall try to describe briefly how the matter stands. First, we try to get clearly in our minds how far the system of classical mechanics has shown itself adequate to serve as a basis for the whole of physics. Since we are dealing here only with the foundations of physics and with its development, we need not concern ourselves with the purely formal progress of mechanics. Equation of Lagrange, canonical equations, etc. One remark, however, appears indispensable. The notion material point is fundamental for mechanics. If now we seek the mechanics of a bodily object, which itself cannot be treated as a material point, and strictly speaking every object perceptible to our senses is of this category, then the question arises, how shall we imagine the object to be built up out of material points, and what forces must we assume as acting between them? The formulation of this question is indispensable if mechanics is to pretend to describe the object completely. It is natural to the tendency of mechanics to assume these material points and the laws of forces acting between them as invariable, since time alterations would lie outside of the scope of mechanical explanation. From this, we can see that classical mechanics must lead us to an atomistic construction of matter. We now realize with special clarity how much in error are those theorists who believe that theory comes inductively from experience. Even the great Newton could not free himself from this error. Hypothesis non fingo. In order to save itself from becoming hopelessly lost in this line of thought atomistic, science proceeds first in the following manner. The mechanics of a system is determined if its potential energy is given as a function of its configuration. Now, if the acting forces are of such a kind as to guarantee maintenance of certain qualities of order of the system's configuration, then the configuration may be described with sufficient accuracy by a relatively small number of configuration variables, QR. The potential energy is considered only in so far as it is dependent upon these variables. For instance, description of the configuration of practically rigid body by 6 variables. A second method of application of mechanics, which avoids the consideration of a subdivision of matter down to real material points, is the mechanics of so-called continuous media. This mechanics is characterized by the fiction that the density of matter and speed of matter is dependent in a continuous manner upon coordinates and time, and that the part of the interactions not explicitly given can be considered as surface forces, pressure forces, which again are continuous functions of location. Herein, we find the hydrodynamic theory and the theory of elasticity of solid bodies. These theories avoid the explicit introduction of material points by fictions which, in the light of the foundation of classical mechanics, can only have an approximate significance. In addition to their great practical significance, these categories of science have, by enlargement of the mathematical world of ideas created, thus formal auxiliary instruments, partial differential equations, which have been necessary for the subsequent attempts at formulating the total scheme of physics in a manner which is new as compared with that of Newton. These two modes of application of mechanics belong to the so-called phenomenological physics. It is characteristic of this kind of physics that it makes as much use as possible of concepts which are close to experience, but which, for this reason, have to give up to a large degree unity and the foundations. Heat, electricity, and light are described by special variables of state and constants of matter order than the mechanical state, and to determine all of these variables in their relative dependence was a rather empirical task. Many contemporaries of Maxwell saw in such a manner of presentation the ultimate aim of physics, which they thought could be obtained purely inductively from experience on account of the relative closeness of the concepts used to the experience. From the point of view of theories of knowledge, Saint-Mill and M. Mach took their stand approximately on this ground. According to my belief, the greatest achievement of Newton's mechanics lies in the fact that its consistent application has laid beyond this phenomenological representation, particularly in the field of heat phenomena. These occurred in the kinetic theory of gases and in a general way in statistical mechanics. The former connected the equation of state of the ideal gases, viscosity, diffusion and heat conductivity of gases, and radiometric phenomena of gases, and gave the logical connection of phenomena which, from the point of view of direct experience, had nothing whatever to do with one another. The latter gave a mechanical interpretation of the order. The latter gave a mechanical interpretation of the thermodynamic ideas and laws, as well as the discovery of the limit of applicability of the notions and laws to the classical theory of heat. This kinetic theory, which surpassed by far the phenomenological physics as regards the logical unity of its foundations, produced moreover the finite values for the true magnitudes of atoms and molecules, which resulted from several independent methods and were thus placed beyond the realm of reasonable doubt. These decisive progresses were paid for by the coordination of atomistic entities to the material points, the constructively speculative character of which entities being obvious. Nobody could, however, to perceive directly an atom. Laws concerning variables connected more directly with experimental facts, for example, temperature, pressure, speed, were deduced from the fundamental ideas by means of complicated calculations. In this manner, physics, at least part of it, originally more phenomenologically constructed, was reduced by being founded upon Newton's mechanics for atoms and molecules to a basis further removed from direct experiment, but more uniform in character. 3. The field concept. In explaining optical and electrical phenomena, Newton's mechanics has been far less successful than it had been in the field cited above. It is true that Newton tried to reduce light to the motion of material points in his corpuscular theory of light. Later on, however, as the phenomena of polarization, diffraction, and interference of light forced upon this theory more and more unnatural modifications, Huygens and undulatory theory of light prevailed. Probably this theory owes its origin essentially to the phenomena of crystallographic optics and to the theory of sound, which was then already elaborated to a certain degree. It must be admitted that Huygens' theory also was based in the first instance upon classical mechanics, but the all-penetrating ether had to be assumed as the carrier of the waves, and the structure of the ether formed from material points could not be explained by any known phenomenon. One could never get a clear picture of the interior forces governing the ether, nor of the forces acting between the ether and the ponderable matter. The foundations of this theory remained therefore eternally in the dark. The true basis was a partial differential equation, the reduction of which the mechanical elements remained always problematic. For the theoretical conception of electric and magnetic phenomena, one introduced again masses of special kind, and between these masses one assumed the existence of forces acting at a distance, similar to Newton's gravitational forces. This special kind of matter, however, appeared to be lacking in the fundamental property of inertia, and the forces acting between these masses and the ponderable matter remained obscure. To these difficulties there had to be added the polar character of these kinds of matter, which did not fit into the scheme of classical mechanics. The basis of the theory became still more unsatisfactory when electrodynamic phenomena became known, notwithstanding the fact that these phenomena brought the physicists to the explanation of magnetic phenomena through electrodynamic phenomena, and in this way made the assumption of magnetic masses superfluous. This progress had indeed to be paid for by increasing the complexity of the forces of interaction which had to be assumed as existing between electrical masses in motion. The escape from this unsatisfactory situation by the by the electric field theory of Faraday and Maxwell represents probably the most profound transformation which has been experienced by the foundations of physics since Newton's time. Again, it has been a step in the direction of constructive speculation which has increased the distance between the foundation of the theory and what can be experienced by means of our five senses. The existence of the field manifests itself indeed only when electrically charged bodies are introduced into it. The differential equations of Maxwell connect the spatial and temporal differential coefficients of the electric and magnetic fields. The electric masses are nothing more than places of non-disappearing divergency of the electric field. Light waves appear as undulatory electromagnetic field processes in space. To be sure, Maxwell still tried to interpret his field theory mechanically by means of mechanical ether models, but these attempts receded gradually to the background following the representation purged of any unnecessary additions by Heinrich Hertz, so that in this theory the field finally took the fundamental position which had been occupied in Newton's mechanics by the material points. At first, however, this applies only for electromagnetic fields as empty space. In its initial stage, the theory was yet quite unsatisfactory for the interior of matter, because their two electric vectors had to be introduced, which were connected by relations dependent on the nature of the medium. These relations, being inaccessible to any theoretical analysis and analogous situation, arose in connection with the magnetic field as well as in the relation between electric current density and the field. Here H.A. Lorentz found an escape which showed at the same time the way to an electrodynamic theory of bodies in motion, a theory which was more or less free of arbitrary assumption. His theory was built on the following fundamental hypothesis. Everywhere, including the interior of ponderable bodies, the seat of the field is the empty space. The participation of matter in electromagnetic phenomena has its origin only in the fact that the elementary particles of matter carry inalterable electric charges, and on this account are subject on the one hand to the actions of ponderomotive forces, and on the other hand possess the property of generating a field. The elementary particles obey Newton's law of motion for the material point. This is the basis on which H.A. Lorentz obtained his synthesis of Newton's mechanics and Maxwell's field theory. The weakness of this theory lies in the fact that it tried to determine the phenomena by a combination of partial differential equations, Maxwell's field equations for empty space, and total differential equations, equations of motion of points, which procedure was obviously unnatural. The unsatisfactory part of the theory showed up externally by the necessity of assuming finite dimension for the particles in order to prevent the electromagnetic field existing at their surfaces from becoming infinitely great. The theory failed, moreover, to give any explanation concerning the tremendous forces which hold the electric charges on the individual particles. H.A. Lorentz accepted these weaknesses of his theory, which were well known to him, in order to explain the phenomena correctly, at least as regards their general lines. Furthermore, there was one consideration which reached beyond the frame of Lorentz theory. In the environment of an electrically charged body, there is a magnetic field which furnishes an apparent contribution to its inertia. Should it not be possible to explain the total inertia of the particles electromagnetically? It is clear that this problem could be worked out satisfactorily only if the particles could be interpreted as regular solutions of the electromagnetic partial differential equations. The Maxwell equations in their original form do not, however, allow such a description of particles because their corresponding solution contains singularity. Theoretical physicists have tried for a long time, therefore, to reach the goal by a modification of Maxwell's equations. These attempts have, however, not been crowned with success. Thus it happened that the goal of erecting a pure electromagnetic field theory of matter remained unattained for the time being, although in principle no objection could be raised against the possibility of reaching such a goal. The thing which deterred one in any further attempt in this direction was the lack of any systematic method leading to the solution. What appears certain to me, however, is that in the foundation of any consistent field theory, there shall not be, in addition, in the concept of field, any concept concerning particles. The whole theory must be based solely on partial differential equations and their singularity-free solutions. 4. The theory of relativity. There is no inductive method which could lead to the fundamental concepts of physics. Failure to understand this fact constitutes the basic philosophical error of so many investigators of the 19th century. It was probably the reason why the molecular theory and Maxwell's theory were able to establish themselves only at a relatively late date. Logical thinking is necessarily deductive. It is based upon hypothetical concepts and axioms. How can we hope to choose the latter in such a manner as to justify us in accepting success as a consequence? The most satisfactory situation is evidently to be found in cases where the new fundamental hypotheses are suggested by the world of experience itself. The hypothesis of the non-existence of perpetual motion as a basis for thermodynamics affords such an example of a fundamental hypothesis suggested by experience. The same thing holds for the principle of inertia of Galileo. In the same category, moreover, we find the fundamental hypothesis of the theory of relativity, which theory has led to an unexpected expansion and broadening of the field theory and to the superseding of the foundations of classical mechanics. The successes of the Maxwell-Lorentz theory have given great confidence in the validity of the electromagnetic equations for empty space and hence, in particular, to the statement that light travels in space with a certain constant speed c, celerity. Is this law of the invariability of light velocity in relation to any desired inertial system valid? If it were not, then one specific inertial system, or more accurately, one specific state of motion of a body of reference, would be distinguished from all others. In opposition to this idea, however, stand all the mechanical and electromagnetic optical facts of our experience. For these reasons, it was necessary to rise to the degree of a principle, the validity of the law of constancy of light velocity for all inertial systems. For this, it follows that the spatial coordinates x1, x2, x3 and the time x4 must be transformed according to the Lorentz transformation, which is characterized by invariance of the expression ds square equal dx1 square plus dx2 square plus dx3 square minus dx4 square, if the unit of time is chosen in such a manner that the speed of light celerity equal 1. By this procedure, time lost its absolute character and was included with the spatial coordinates of algebraically similar character. The absolute character of time and particularly of simultaneity were destroyed, and the four-dimensional description became introduced as the only adequate one. In order to account also for the equivalence of all inertial systems with regard to all the phenomena of nature, it is necessary to postulate invariance of all systems of physical equations which express general laws with regard to the Lorentzian transformation. The elaboration of this requirement forms the content of the special theory of relativity. This theory is compatible with the equations of Maxwell, but it is incompatible with the basis of classical mechanics. It is true that the equations of motion of the material point can be modified, and with them the expression for momentum and kinetic energy of the material point, in such a manner as to satisfy the theory, but the concept of the force of interaction, and with it the concept of potential energy of a system, lose their basis because their concepts rest upon the idea of absolute instantaneousness. The field as determined by differential equations takes the place of the force. Since the foregoing theory allows interaction only by fields, it requires a field theory of gravitation. Indeed, it is not difficult to formulate such a theory in which, as in Newton's theory, the gravitational fields can be reduced to a scalar, which is the solution of a partial differential equation. However, the experimental facts expressed in Newton's theory of gravitation lead in another direction, that of the general theory of relativity. Classical mechanics contains one point which is unsatisfactory, in that, in the fundamentals, the same mass constant is met twice over in two different roles, namely as inertial mass in the law of motion and as gravitational mass in the law of gravitation. As a result of this, the acceleration of a body in a pure gravitational field is independent of its material, or in a coordinate system of uniform acceleration, accelerated in relation to an inertial system. The motions take place at the would in a homogeneous gravitational field in relation to a motionless system of coordinates. If one assumes that the equivalence of these two cases is complete, then one attains an adaptation of our theoretical thinking to the fact that the gravitational and inertial masses are identical. From this, it follows that there is no longer any reason for favoring as a fundamental principle the inertial systems, and we must admit as equivalent in their own right also nonlinear transformation of the coordinates x1, x2, x3, x4. If we make sure transformation of system of coordinates of the special theory of relativity, then the metric ds square equal dx1 square plus dx2 square plus dx3 square minus dx4 square goes over to a general Riemannian metric of Bahn. ds square equals g mu y dx mu and dxy summed over mu and v, v, not y, where the g mu v symmetrical in mu, and v, and certain function of x1 to x4, which describe both the metric property and the gravitational field in relation to the new system of coordinates. The foregoing improvement in the interpretation of the mechanical basis must must, however, be paid for in that, as becomes evident on closer scrutiny, the new coordinates could no longer be interpreted as results of measurements by rigid bodies and clocks, as they could in the original system, an inertial system with vanishing gravitational field. The passage to the general theory of relativity is realized by the assumption that such a representation of the field properties of space are already mentioned by function G mu v, that is to say by a Riemann metric, is also justified in the general case in which there is no system of coordinates in relation to which the metric takes the simple quasi-Euclidean form of the special theory of relativity. Now the coordinates by themselves no longer express metric relation, but only the neighborliness of the things described, whose coordinates differ but little from one another. All transformations of the coordinates have to be admitted so long as these transformations are free from singularities. Only such equations as are covariant in relation to arbitrary transformations in this sense have meaning as expressions of general laws of nature, postulate of general covariancy. The first aim of the general theory of relativity was a preliminary statement which, by giving up the requirement of constituting a closed thing in itself, could be connected in as simple a manner as possible with the facts directly observed. Newton's gravitational theory gave an example by restricting itself to the pure mechanics of gravitation. This preliminary statement may be characterized as follows. 1. The concept of the material point of its mass is retained. A law of motion is given for it. This law of motion being the translation of the law of inertia into the language of the general theory of relativity. This law is a system of total differential equations, the system characteristic of the geodetic line. 2. In place of Newton's law of interaction by gravitation, we shall find the system of the simplest generally covariant differential equation which can be set up for the G mu v tensor. It is formed by equating to zero the once contracted Riemann curvature tensor R of mu v equals 0. This formulation permits the treatment of the problem of the planets. More accurately speaking, it allows the treatment of the problem of motion of material points of practically negligible mass in the gravitational field produced by a material point, which itself is supposed to have no motion central symmetry. It does not take into account direction of the moved material points on the gravitational field, nor does it consider how the central mass produces this gravitational field. Analogy with classical mechanics shows that the following is a way to complete the theory. One set up as field equation REK minus 1/2 G alpha R equal minus T alpha, where R represents the scalar of Riemannian curvature, T alpha the energy tensor of the matter in a phenomenological representation. The left side of the equation is chosen in such as manner that its divergence disappears identically. The resulting disappearance of the divergence of the light side produces the equations of motion of matter in the form of partial differential equations for the case where T alpha introduce for the description of the matter only four further functions independent of each other. For instance, density, pressure, and velocity components, where there is between the latter an identity, and between pressure and density an equation of condition. By this formulation, one reduces the whole mechanics of gravitation to the solution of a single system of covariant partial differential equations. The theory avoids all internal discrepancies which we have charged against the basis of classical mechanics. It is sufficient, as far as we know, for the representation of the observed facts of celestial mechanics, but it is similar to a building, one wing of which is made of fine marble, left part of the equation, but the other wing of which is built of low-grade wood, right side of equation. The phenomenological representation of matter is in fact only a crude substitute for a representation which would correspond to all known properties of matter. There is no difficulty in connecting Maxwell's theory of the electromagnetic field with the theory of the gravitational field, so long as one restricts himself to space free of ponderable matter and free of electric density. All that is necessary is to put on the right-hand side of the above equation for tensor T alpha the energy tensor of the electromagnetic field in empty space, and to associate with the so modified system of equations the Maxwell field equation for empty space written in general covariant form. Under these conditions, there will exist between all these equations a sufficient number of the differential identities to guarantee their consistency. We may add that this necessary formal property of the total system of equations leaves arbitrary the choice of the sign of the member tensor alpha, a fact which was later shown to be important. The desire to have for the foundations of the theory the greatest possible unity has resulted in several attempts to include the gravitational field and the electromagnetic field is one formal but homogeneous picture. Here we must mention particularly the five-dimensional theory of Kaluza and Klein. Having considered this possibility very carefully, I feel that it is more desirable to accept the lack of internal uniformity of the original theory, because I do not consider that the totality of the hypothetical basis of the five-dimensional theory contains less of an arbitrary nature than does the original theory. The same statement may be made for the projectile variety of the theory, which has been elaborated with great care, in particular by Vedantzig and by Pauli. The foregoing consideration concern exclusively the theory of the field free of matter. How are we to proceed from this point in order to obtain a complete theory of atomically constructed matter? In such a theory, singularities must certainly be excluded, since without such exclusion the differential equations do not completely determine the total field. Here in the field theory of general relativity, we meet the same problem of a theoretical field representation of matter as was met originally in connection with the pure Maxwell theory. Here again, the attempt to construct particles out of the field theory leads apparently to singularities. Here also, the endeavor has been made to overcome this defect by the introduction of new field variables and by elaborating and extending the system of field equations. Recently, however, I discovered in collaboration with Dr. Rosen that the above mentioned simplest combination of the field equation of gravitation and electricity produce centrally symmetrical solutions which can be represented as free of singularity. The well-known centrally symmetrical solution of Schwarzschild for the pure gravitational field, and those of Resner for the electric field with consideration of its gravitational action. We shall refer to this shortly in the paragraph next but one. In this way, it seems possible to get for further and its interactions a pure field theory free of additional hypotheses. One moreover whose test by submission to facts of experience does not result in difficulties other than purely mathematical ones, which difficulties, however, are very serious. 5. Quantum theory and the fundamentals of physics. The theoretical physicists of our generation are expecting the erection of a new theoretical basis for physics, which would make us of fundamental concepts greatly different from those of the field theory considered up to now. The reason is that it has been found necessary to use for the mathematical representation of the so-called quantum phenomena new sorts of methods of consideration. While the failure of classical mechanics as revealed by the theory of relativity is connected with the finite speed of light, it's avoided of being infinite, it was discovered at the beginning of our century that there were other kinds of inconsistencies between deductions from mechanics and experimental facts, which inconsistencies are connected with the finite magnitude, the avoidance of being zero, of Planck's constant h. In particular, while molecular mechanics requires that both heat content and monochromatic radiation density of solid bodies should decrease in proportion to the decreasing absolute temperature, experience has shown that they decrease much more rapidly than the absolute temperature. For a theoretical explanation of this behavior, it was necessary to assume that the energy of a mechanical system can't assume any sort of value by only certain discrete values whose mathematical expression were always dependent upon Planck's constant h. Moreover, this conception was essential for the theory of the atom, Bohr's theory, for the transitions of the states into one another with or without emission of or absorption of radiation. No causal laws could be given, but only statistical ones, and a similar conclusion holds for the radioactive decomposition of atom, which decomposition was carefully investigated about the same time. For more than 2 decades, physicists tried vainly to find a uniform interpretation of this quantum character of systems and phenomena. Such an attempt was successful about 10 years ago. Thus, the agency of two entirely different theoretical methods of attack. We owe one of these to Heisenberg and Dirac, and the other to de Broglie and Schrödinger. The mathematical equivalence of the two methods was soon recognized by Schrödinger. I shall try here to sketch the line of thought of de Broglie and Schrödinger, which lies closer to the physicist method of thinking, and shall accompany the description with certain general considerations. The question is first, how can one assign a discrete succession of energy value H0 to a system specified in the sense of classical mechanics? The energy function is given function of the coordinate QR and the corresponding momenta PR. Planck's constant h relates the frequency h HO or H slash H to the NH gamma slash H or to the energy values H gamma. It is therefore sufficient to give to the system a succession of discrete frequency values. This reminds us of the fact that in acoustics, a series of discrete frequency values is coordinated to a linear partial differential equation if boundary values are given, namely the sinusoidal periodic solution. In corresponding manner, Schrödinger set himself the task of coordinating a partial differential equation for a scalar function phi to the given energy function epsilon qr pr couple, where the qr and the time t are independent variables. In this he succeeded for a complex function phi in such a manner that the theoretical values of the energy H gamma as required by the statistical theory actually resulted in a satisfactory manner from the periodic solution of the equation. To be sure, it did not happen to be possible to associate a definite movement in the sense of mechanics of material points, which a definite solution phi couple QRT of the Schrödinger equation. This means that the phi function does not determine at any rate exactly the story of the QR as functions of the time t. According to Born, however, an interpretation of the physical meaning of the phi function was shown to be possible in the following manner. Phi or phi factor phi, the square of the absolute value of the complex function phi is the probability density at the point under consideration in the configuration state space of the QR at the time t. It is therefore possible to characterize the content of the Schrödinger equation in a manner easy to be understood, but not quite accurate, as follows. It determines how the probability density of a statistical ensemble of systems varies in the configuration state space with the time. Briefly, the Schrödinger equation determines the alteration of the function phi of the QR with the time. It must be mentioned that the result of this theory contains as limiting values the result of the particle mechanics if the wavelength and wave straight length encountered during the solution of the Schrödinger problem is everywhere so small that the potential energy varies by a practically infinitely small amount for a change of one wave straight length in the configuration state space. Under this condition, the following can in fact be shown. We choose a region GO in the configuration state space, which although large in every dimension in relation to the wavelength, is small in relation to the practical dimensions of the configuration space. Under this condition, it is possible to choose a function of phi for initial time t0 in such a manner that it vanishes outside of the region G0 and behaves according to the Schrödinger equation in such a manner that it retains this property approximately at least also for a later time. But with the region G0 having passed at that time t into another region G, in this manner, one can, with a certain degree of approximation, speak of the motion of the region G as a whole, and one can approximate this motion by the motion of a point in the configuration state space. This motion then coincides with the motion which is required by the equations of classical mechanics. Experiments on interference made with particle rays have given a brilliant proof that the wave character of phenomena of motion as assumed by the theory does really correspond to the facts. In addition to this, the theory succeeded easily in demonstrating the statistical laws of the transition of a system from one quantum condition to another under the action of external forces, which from the standpoint of classical classical mechanics appears as a miracle. The external forces were here represented by small additions of the potential energy as functions of the time. Now, while in classical mechanics, such additions can produce only correspondingly small alterations of the system. In the quantum mechanics, they produce alteration of any magnitude, however large, but with correspondingly small probability. A consequence in perfect harmony with experience. Even an understanding of the laws of radioactive decomposition, at least in their broad lines, was provided by the theory. Probably never before has a theory been evolved which has given a key to the interpretation and calculation of such a heterogeneous group of phenomena of experience as has the quantum theory. In spite of this, however, I believe that the theory is apt to beguile us into error in our search for a uniform basis for physics, because in my belief it is an incomplete representation of real things, although it is the only one which can be built out of the fundamental concepts of force and material points. Quantum corrections to classical mechanics. The incompleteness of the representation is the outcome of the statistical nature and completeness of the laws. I will now justify this opinion. I ask first, how far does the phi function describe a real condition of a mechanical system? Let us assume the phi to be the periodic solution, but in the order of increasing energy values of the Schrödinger equation. I shall leave open for the time being the question as to how far the individual phi are complete description of physical conditions. A system is first to the condition phi1 of lowest energy 1. Then, during a finite time, a small disturbing force acts upon the system. At a later instant, one obtains then from the Schrödinger equation a phi function of the form phi equals sigma celerity r phi r, where the CR are complex constants. If the phi r are normalized, then valor absolu C1 is nearly equal to 1. Valor absolu C2, etc. is small compared with 1. One may now ask, does phi describe a real condition of the system? If the answer is yes, then we can hardly do otherwise than ascribe to this condition a definite energy and in particular such an energy as exceeds A1 by a small amount, in any case A1 inferior to A2. Such an assumption is, however, at variance with the experiments on electron impact such as have been made by J. Frank and J. Hertz. If in addition to these one accepts Millikan's demonstrations of the discrete nature of electricity, as a matter of fact, these experiments lead to the conclusion that energy values of a state lying between the quantum values of a state lying between the quantum values do not exist. From this it follows that our function phi does not in any way describe a homogeneous condition of the body, but represents rather a statistical description in which the CR represent probabilities of the individual energy values. It seems to be clear, therefore, that the born statistical interpretation of the quantum theory is the only possible one. The phi function does not in any way describe a condition which could be that of a single system. It relates rather to many systems, to an ensemble of systems, in the sense of statistical mechanics. If except for certain special cases, the phi function furnishes only statistical data concerning measurable magnitudes. The reason lies not only in the fact that the operation of measuring introduce and count elements which can be grasped only statistically, but because of the very fact that the phi function does not in any sense describe the condition of one single system. The Schrödinger equation determines the time variations which are experienced by the ensemble of systems which may exist with or without external action on the single system. Such an interpretation eliminates also the paradox recently demonstrated by myself and two collaborators, and which relates to the following problem. Consider a mechanical system constituted of two partial systems A and B, which have interaction with each other only during limited time. They let the phi function before their interaction be given. Then the Schrödinger equation will furnish the phi function after the interaction has taken place. Let us now determine the physical condition of the partial system A as completely as possible by measurements. Then the quantum mechanics allows us to determine the phi function of the partial system B from the measurements made and from the phi function of the total system. This determination, however, gives a result which depends upon which of the determining magnitudes specifying the condition of A has been measured, for instance, coordinates or momenta. Since there can be only one physical condition of B after the interaction and which can reasonably not be considered as depend on the particular measurement we perform on the system A separated from B, it may be concluded that the phi function is not ambiguously coordinated with the physical condition. This coordination of several phi functions with the same physical condition of system B shows again that the phi function can't be interpreted as a complete description of a physical condition of a unique system. Here also the coordination of the phi function to an ensemble of systems eliminates every difficulty. The fact that quantum mechanics affords, in such a simple manner, statements concerning apparently discontinuous transitions from one total conditions to another without actually giving a representation of the specific process. This fact is connected with another, namely, the fact that the theory in reality does not operate with the single system, but with the totality of systems. The coefficients CR of our first example are really altered very little under the action of the external force. With this interpretation of quantum mechanics, one can understand why this theory can easily account for the fact that weak disturbing forces are able to produce alterations of any magnitude in the physical condition of a system. Such disturbing forces produce indeed only correspondingly small alterations of the statistical density in the ensemble of systems, and hence only infinitely weak alteration of the phi functions, the mathematical description of which offers far less difficulty than would be involved in the mathematical representation of finite alterations experienced by part of the single systems. What happens to the single system remains, it is true, entirely unclarified by this mode of consideration. This enigmatic happening is entirely eliminated from the representation by the statistical manner of consideration. But now I ask, is there really any physicist who believes that we shall never get any inside view of these important alterations in the single system, in their structure and their causal connections, and is regardless of the fact that these single happenings have been brought so close to us, thanks to the marvelous inventions of the Wilson chamber and the Geiger counter, to believe this is logically possible without contradiction, but it is so very contrary to my scientific instinct that I can't forego the search for a more complete conception. To this consideration, we should add those of another kind, which also voice their play against the idea that the methods introduced by quantum mechanics are likely to give a useful basis for the whole of physics. In the Schrödinger equation, absolute time and also the potential energy play a decisive role, while these two concepts have been recognized by the theory of relativity as inadmissible in principle. If one wishes to escape from this difficulty, he must found the theory upon field and field laws instead of upon forces of interaction. This led us to transpose the statistical methods of quantum mechanics to fields, that is, to systems of infinitely many degrees of freedom, although the attempts so far made are restricted to linear equations, which, as we know from the results of the general theory of relativity, are insufficient. The complications made up to now by the very ingenious attempts are already terrifying. They certainly will rise sky high if one wishes to obey the requirements of the general theory of relativity, the justification of which in principle nobody doubts. To be sure, it has been pointed out that the introduction of a space-time continuum may be considered as contrary to nature in view of the molecular structure of everything which happens on a small scale. It is maintained that perhaps the success of the Heisenberg method points to a purely algebraical method of description of nature, that is, to the elimination of continuous functions from physics. Then, however, we must also give up by principle the space-straight time or the space-time continuum. It is not unimaginable that human ingenuity will someday find methods which will make it possible to proceed along such a path. At the present time, however, such a program looks like an attempt to breathe in empty space. There is no doubt that quantum mechanics has seized hold of beautiful elements of truth, and that it will be a test stone for any future theoretical basis, and that it must be deducible as a limiting case from that basis, just as electrostatics is deducible from the Maxwell equations of the electromagnetic field, or as thermodynamics is deducible from classical mechanics. However, I do not believe that quantum mechanics will be a starting point in the search for this basis, just as vice versa. One could not go from thermodynamics, statistical mechanics, to the foundations of mechanics. In view of this situation, it seems to be entirely justifiable seriously to consider the question as to whether the basis of field physics can't by any means be put into harmony with the facts of the quantum theory. Is this not the only basis which, consistently with today's possibility of mathematical expression, can be adapted to the requirements of the general theory of relativity? The belief prevailing among the physicists of today that such an attempt will be hopeless may have its root in the unjustifiable idea that such a theory should lead as a first approximation to the equations of classical mechanics for the motion of corpuscles, or at least to total differential equations. As a matter of fact, up to now, we have never succeeded in representing corpuscles theoretically by fields free of singularities, and we can a priori say nothing about the behavior of such entities. One thing, however, is certain.